Hey class, we are going to do a quick intro to Unit 1 Notes Day 4. To get us ready, these notes are a little long, so you need an intro. We've talked about some of this already, so let's just get it officially down into our notes. So an index, when I'm talking about radicals, if I have the nth root of a, the index is n. So it's that little number out in front of the radical. And so if I had like a fourth root, I would be wondering what number multiplied by itself 4 times gives me whatever the number is underneath the radical. So in a square root, which looks like this, the index is 2. It's an invisible index. All right, we don't have to write the 2 there, so we don't. But in a cube root, the index is 3. So once it's a cube root or above, we put that little number right before the radical, and that is our index. When I reduce radicals, I think that the easiest way to go about this, which we've talked about on worksheet 1, is to find the biggest perfect square that goes into the number underneath the radical, right? So for example, the biggest perfect square that goes into 108 is actually 36. Okay, 36 times 3 is 108. Now, 4 does go into 108, but it's not the biggest perfect square. The biggest perfect square that goes into 108 is 36, which is why I chose that. I am now going to square root both of these, and the square root of 36 is 6, and the square root of 3 doesn't come out nice, so I leave it. But what about cube roots? What if I'm reducing a cube root? I do not want to look for a perfect square if I'm going to reduce a cube root. I want to look for a perfect cube. So that means I have to know some of my perfect cubes. All right, so what are the perfect cubes? Well, to list them, you don't have to memorize them. Just in your head, do 1 cubed. 1 cubed is 1. 2 cubed is 8. 3 cubed, 27. 4 cubed, 64. And 5 cubed is 125. Now, it would be beneficial to maybe know more of these, but off the top of your head, if you know these perfect cubes, you probably will be okay, because we're not going to give you these massive numbers. We will give you numbers that likely have one of these 5 numbers that go into it. So, 81. It's not 9 times 9 this time. Now, you could break it down 9 times 9, and then 3 times 3. This is the way I don't like. And then since it's a cube root, you're going to look for groups of 3 rather than groups of 2. Okay? I don't like that way. This is the way I would do this. 27 times 3 is 81. Okay? And notice that 27 is a perfect cube. So now instead of square rooting both of these numbers, I'm going to cube root both of these numbers. The cube root of 27 is 3. And the cube root of 3 is not nice. So I'm going to just leave this as 3 cube root 3. And that's my answer. So it's the same idea as square roots. It's just instead of looking for perfect squares, I'm going to look for perfect cubes. All right, so we also talked about the next part. So this is just the official notes on it. We know that if I have x to the m over n, that the denominator becomes my index and my numerator is what we're going to raise the base to. Now remember, I could also rewrite this as this, where first I take the root and then I raise it to the power. Either way, it's correct. But let's convert to radical form. So for this first one, this is just cube root of x. The next one would just be square root of y. Okay, the third one would be the cube root of x squared. I could write it as the cube root of x and then squared. Both of those are acceptable answers. The fifth root of a to the fourth. Be careful. This negative is going to stay outside because the only thing being raised to the 5/8 is the x. So the negative stays outside, and then I'm going to have the 8th root of x to the 5th. I'll stop there. I'll do the rest with you in class for this example, but for the next example, let's write in exponential form. I'll do the first 2 with you. This would be x to the 1/3. And this one's going to be x to the 3/4. Remember, the index becomes the denominator. So if I asked for writing in exponential form, this would be exponential. If I give you a problem and the original problem is in radical form, that means that I need my answer to be in radical form. So you're going to stay with the same form of the original problem, okay? And this is going to be my last example from the video, just as an intro, and then we will do the rest in class. But this is going to be reducing radicals with larger indexes than 2, including variables. So this is kind of the long way, and we'll talk about shortcuts in class. What you want to do is break up the number underneath the radical to be a perfect cube and then a non-perfect cube, unless the number itself is a perfect cube, which 27 is. So I don't have to break up 27 because it is cube rootable. So I can rewrite this like so. The cube root of 27 times the cube root of x to the 5th, right? So the cube root of 27 is 3. What's the cube root of x to the 5th? Well, this I am going to break up. I'm going to break this up into something I can cube root and something maybe I can't. But to kind of explain that better, let's go ahead and think about what does x to the 5th actually mean? It means this. I hope you can all agree that x to the 5th means x times x times x times x times x 5 times. All right, so let's rearrange this a little bit. I hope you guys can agree that I can rewrite this as x cubed times x squared, right? Because there's 2 x's left over. Now, if I multiplied those back together, I would add my exponents and I would get back to x to the 5th. So at this point, I am actually going to cube root both of these. Okay? The cube root of x cubed, those cubes just cancel out. It's just x. I cannot simplify the cube root of x squared. There has to be at least 3 x's in that radical for me to reduce it further. Okay, and the reason why the number is 3 is because that's the index. If the index was 4, I would need at least 4 x's in order to reduce it further. So since there's only 2 x's under the radical, that can no longer be simplified. I'm going to drop this 3 down. So my final answer is 3x cube root of x squared. Yes, that might be a little confusing. That's why I'm introing it to you on this video, and we're going to talk about it more in class altogether. But hopefully that gives you a little taste of what's to come.